Hello, I am Dio, and we'll be talking about AVL trees, mainly about I'll show an example of insertion, and we'll mainly talk about rotation and how we balance AVL trees after insertion or deletion. We'll see what is an AVL tree. So AVL tree is just a binary search tree where each vertex or node belonging to the tree has a balance factor -1, 0, or 1. So it's basically saying if one of the part of the subtree, the left subtree or the right subtree, like both of them should not be one heavy sided. So that's basically it. So this helps in making the AVL tree balanced. AVL tree was invented by G.M. Adelson, Welsky, and E.M. Landis in 1962. That's why it's called AVL. And AVL tree is a height balanced tree in which for every internal position of T, the heights of the children of P differ by at most 1. And okay, yeah, of course, every subtree of an AVL tree is also an AVL tree in itself. And the height of an AVL tree is kept small using height balance property. Which is so the height of an AVL tree of n entries is always log n, which is okay. Insertion in an AVL tree is the same as in a binary tree, but after we insert something, just like in a binary tree, we will have to rebalance the AVL tree using rotations. So that's what we're going to talk about. There are 4 different concepts of rotation. Okay, we are not going to this is not exactly what's going to happen in the code, but these are concepts which we use for visualization to write the code. So first we have single left operation. A single left operation is applied when a node is inserted in the right subtree of a right subtree. So right. Single right rotation. A single right rotation is applied when a node is inserted in the left subtree of a left subtree, and then left right. It is also okay. This is like so there in some of the websites, in some of the in places they use double right instead of left right, and instead of right left they use double left. So this might be confusing at times, but don't worry, it's the same thing. Left right is like just double right, and right left is just double left. Okay, so left right is a combination of left and right followed by right, and this happens when a node is inserted to the right subtree of the left subtree, and right left is the same thing, but when a node is inserted into the left subtree of the right subtree. In all these cases, when insertion happens, there is the balance of the tree is disturbed. That's why we use these rotation techniques. This is a single right rotation concept. So the left subtree. Okay, so we know this is our main node, parent node. This is our X, and this is our C, and this is heavy. This is heavy on the left side, and the left subtree of the left subtree, when a node is inserted into the left subtree of the left subtree and it causes an imbalance, this is called as the single right rotation. And what we'll do in this is so what we're going to do now is we're going to just form a single right rotation. X will we are rotating this, and then we are also rotating this, and this will go here. So it's basically we are rotating everything. So and this is what the final answer will be. So what is happening is X is rotated right, C is also rotated right, and then B is also rotated right, and so B comes here, and then this is wrong. This should be B, and this should probably be A. So it's okay, it's fine, and we'll talk about the example in the next slide. So this is an example. Okay, this is a representation of how it will happen. So A, B, C, and because this balance factor cannot be 2. It should be either -1, 0, or 1. So this is an unbalanced tree. So what will happen, because because of an insertion to the left subtree of a left subtree, so there's an imbalance. So we'll use single right rotation. Again, this will go here, this will come here, and this will go here. Simple, and it becomes ABC. We'll be talking about the left-right rotation. Okay, so this is our left-right rotation. Okay, so our V becomes unbalanced because the height of this thing is h minus 2, and this will be total because this is h, and there'll be an imbalance created, and this will be imbalanced. So the node which is imbalanced, we go from here, we go left, and then we go right. And this is the node which is causing the imbalance, where it contains an extra node like to the height. So this is left, we're going left, and this is right. And this is how I usually identify if you have to use left right or right left. With practice, within half a second you will understand if it's left right or right left. Okay, so so what is happening first? What we are going to do is we are going to perform a left operation. So what's going to happen is we are going to perform a left operation where this will go here, x will come down, B will go up, and then after and this becomes W, and now again a right operation where W will go here, B will come here, and V will come down, and A will also go down, and our final result will be this. So our W is going, so first it's going left, and then it's going right, and our B is also first it's going left to position W, and then it's going right, it's going into V. V node. It's a bit different, but you just have to remember it. And then a C gets attached to X. This gets attached to X, and that's it. We look at an example. Okay. Okay, this is an example of left right. So this is imbalanced because this is 2. This is so this is left, and we go right, so left right. So now we again perform left right. So what we are going to do is we rotate this, so this will go here, this goes left, this comes back, this goes left, and yeah, and so it's performing like this, it's going left like this, and so B and A will be interchanged, and it will be the shape will be like this. And then now it's still not it's still unbalanced, and now we perform, so it becomes a right operation, sorry, a right operation now, because there's an imbalance in the left of subtree of a left subtree, and we just rotate it right. So C will come down, B will go up, and A will also go one level up. So this becomes our final tree which is balanced. Okay, so let's talk about single left rotation. Same thing here. So when does this happen? When there's an insertion in the right subtree of a right subtree. So this is the right subtree of a right subtree X. So here we use a left operation. It's quite simple. We just rotate everything by left. So this will go up, this will go up, this will come down, and B will get attached to V. So this is our final subtree. Here is an example of a single left rotation. So A, B, C. This is imbalanced because it's -2. So what will happen is you just rotate it left once, and this will go here, and this will also go here. So that this is the right-left rotation concept. So there's an imbalance caused due to an insertion in the left subtree of a right subtree. So this is our right subtree, and this is our left subtree of x. So first we'll perform a right operation. This will go here. X will come down, and then C will also go to the right. We don't need to worry about C. It's fine. And when this is W and X is here, we perform a left operation. This will go here, B will come down. And there is an error in this diagram. I'm very sorry about it, but this should be V, and this should be X, because X is getting right rotated and it will go down. So X is here, and W is up, and then V is getting left rotated, so V will come this side. That's okay. Now we'll look at an example of a right-left operation. It's not example, but still. Okay, so because this is -2 and this is our imbalanced tree, so we go right and we go left, and we know that we have to do a right-left operation. This is how I identify everything, though I do not, it's not right, this is not how you do it, but still it's quite fast when you see, just look at it, it's right, and you go left, and you know that you have to do right-left operation. So what are we doing here? So first we do a right operation. This will go here, C will come down. So that's why it's like this, it becomes this. And then now it's a simple left rotation, single left rotation. A will come down, B will go up, and C will also go up. And that's why it becomes A, B, and C. And this should be 0. Yes, and this is how we do a right-left operation. So we will look at an AVL tree insertion example. We will insert 56, 26, 78, 13, 6, 20, 40, 80, 71, and 60, and we'll be looking at all the rotation in this example. Okay, so first we are inserting 56. Okay, after insertion, okay, this is our parent node, the top node, and now we insert 26. 26 is here. This should be 0. Now we insert 78, 0, 0, 0, and now we insert 13. 13 comes here. This becomes 0. This is 1, 1, 0, and now we insert 6. Okay, this insertion is exactly as the same how we do in a binary search tree. Because 26 is less than 56, we are inserting into the left subtree. 78 is greater than 56, so we are inserting it into the right subtree. And now because 13 is less than 56, it will go to the left subtree, and it is less than 26, so it will go again to the left subtree, which is causing now this is balanced. It's still balanced because it's 0, it's between -1, 0, and 1. And now because when we insert 6, this becomes 2, now it becomes imbalanced, and this becomes a right rotation. So what is going to happen? So this is a right rotation, so this will go here, 26 will come down, and 6 will go up. So this is our right rotation. We are not, this does not come into consideration. We are not rotating any parts of this, only we are rotating only this 3 nodes here. So it becomes 6, 3, 26, and now we insert 20, and 20 is greater than 13, so it will go to the right subtree, but it's less than 26, so it will go to the left subtree of 26. So let's go to the next page. Our balance factor, where this is 2. So we go left, we go right, and this is where our the insertion of the node there, it's causing a problem. So what we are going to do is we are going to do a left operation. So this will go here, 13 will come down, 6 will come down, and after 26 is here, we will perform a right operation, and then 56 will also come down. And what will happen is 26 is here, 13 is here. Because of a right operation, 6 and 13 comes back again. So 6, 13, and 20 gets attached to 13, and then 56 and 78 gets pushed down. So the next step is we are inserting, okay, first we are inserting 40. So 40 is inserted. There is no problem here, and now we are inserting 80. Let's just write the height of the trees, the balance factor. So this is 0. This is -1 because there's a node, there's only one right node, and this will become, this will also become -1, and this will also be -1. So at this point the tree is balanced, and now we go and insert the next number, which is 71. So now we insert 71, and there's no imbalance caused here because this is 0, 0, this is also 0, this is 0, this is -1 because of an extra layer here. This is also -1, this is 0, 0, and 0. But when we insert 60, an imbalance occurs. So this is our 0, so this is again 0, but this is 1, this becomes 1 as well, but now this here becomes -2, this also becomes -2, and this becomes 0, this becomes 0, this is also 0. So now we know that there's an imbalance, because there's an imbalance occurring 56, there's also the balance factor is also affected for the parent tree. So now from 56, so how do we know it's a right left operation? Because after inserting node to the left subtree of a right subtree, if there is an imbalance which occurs, and that's called a right left operation. We can see this is right and this is left. So that's how I usually identify it. Just quickly, wherever the balance factor is not -1, 0, and 1, from that point onwards, go right left, and if it's right left, it's right left operation. If it's left right, it's left right operation. That's the fastest, like that works all the time. That trick works all the time, and it's good to use it. Usually don't use it when you're try not to use it, but this is a good way to understand, easy way to do this very fast. So now what will happen is, so what we are going to do is we are going to first right rotate, this comes down, this 80 comes down, 60 goes up, and this will be 71. This will be 71, and now 71 will go left, and 56 will come down, 40 will also come down. These are not getting affected, and because of that 56 and 40 comes down, 60 gets attached to 56, and 78 and 80, because once we do left, so once we do right and we do left operation again, it comes back again. Or you can just ignore 78 and 80 as well. Like, you don't have to remember that because there's a right rotation and again it's a left rotation, it comes back up. Like, there's no need to, but yeah, it's fine. So why don't we balance this tree? So so this is 0, of course, this is -1, this is 0, this is 0, this is also 0, This is also 0 because you can see this is one level, two level, both levels. So the height is same. Um, is the okay? Yeah, this should be -1 because there's an extra level here. Uh, extra no, the height is yeah, the right subtree height is 1 higher, and this will be 0. This will be 0. This will also be 0. Now our AVL tree is balanced and our insertion operation is done. So we're not going to show AVL tree deletion, but we're going to explain how it's done. It's same as in a binary search tree. We perform deletion same as in a binary search tree, but when deletion happens, the balance of the tree may get disturbed, and we will need to rebalance the tree exactly how we did in insertion. We use rotations to balance the tree. There's no difference between there's not much. The main difference between insertion and deletion is the insertion and deletion itself. The balance of, like, after each insertion and deletion, we need to check if it's balanced, and we also need to balance it, and which is same in both. And both insertion and deletion are similar to binary search tree. Okay, so let's talk about the running times for AVL trees. First, we'll talk about the find. The find is O log n because the height of the AVL tree is log n. And for insertion, we first have to find where we need to insert it, and that will take log n operations. And the restructuring, the rebalancing of the tree will take log n operations. And because, like, if it's the time complexity is O log n for initial find and the restructuring of the AVL tree, and when we add two of the same class, the final result is also belongs to the same class, O log n. And deletion is also the same. We are the initial find that we need to use becomes log n, and the restructuring of the tree is log n, and the final result is also log n. It belongs to the class of logarithmic of n. Thank you for watching this video. If you have any advice or on this tutorial, if you want me to make any changes, you can comment in the video below.